Good morning. I'm a little bit behind. I had intended to get this video done last night, but let's just get going on it. So, to kind of make up for having our exam on Wednesday, I'm recording this section, and then we have two more sections to talk about, and we'll see how far I get. But here's 16.1 vector and gradient fields. So, what is a vector field? Well, these are functions that assign vectors to points in space. So what we'll see some graphics of it. So they can be used to find work done by a force field moving along an object. You're going to see a wind can be listed as a vector field. Flow of fluids through a pipe, there's a vector field. Down through a river, we have two-dimensional vector fields. We also have three-dimensional vector fields. And we're going to connect what we did earlier with single, double, and triple integrals to these vector fields. Okay. So here's an example. You can see here a vector field. This is maybe some of you will recognize this is San Francisco Bay Area. I think this is the Golden Gate Bridge right here, as you can see. So this is vectors of the wind velocity, the wind speed and direction, 10 meters above the surface. And this one here is in the evening at 6 p.m. So you get the strong wind coming here. I guess across, that's the Golden Gate Bridge, right? And various ones here. Earlier in the day, 12 hours early at 6 a.m., it was a very different pattern, not as strong coming into the bay. In fact, looks like the direction of the arrows, wind was blowing out to the sea. By evening time, it's blowing from the sea inwards toward the land. So this is what a vector field looks like. The size of the arrows, again, in a vector, represent the magnitude. In this case, the wind velocity, and the direction indicates the direction. Okay. We can also use it for various other things. Water currents here, so vector fields being shown at how the water is flowing around this. I don't know that it's an island. It's a sort of a peninsula. It is attached, Nova Scotia. You could also use it to represent the air over a wing, an airfoil. So vector fields, speed, could be force. I guess you could even have vectors representing temperatures if you have movement of heated air. Okay, so it's also, a vector field could be called a force field if it associates a force with the vector. So where the length of the vector represents how much force. So stuff like gravity is a force field. So our first definition, let D be a set in 2 dimensions, a plane region, that the vector field on this function f assigns to each point x and y a 2-dimensional vector field, or vector. Okay, so we're going to take some point so each point will get a vector assigned to it. So it'll have a magnitude and a direction. This point over here may have a different, maybe a shorter one, not as much, but a different direction. And again, this is just a randomly assigned one for myself, but we could have a function that actually does this. So it takes the coordinates x and y, so the x coordinate, the y coordinate. This one might be, say, 2, -1, and then from plugging the x and the y in, we get a function that gives us the magnitude and the direction. It gives us a vector. Okay, this one might be 4, +2, something like that. So there's coordinates associated with each point. Those are the x and y coordinates. They get plugged into the function that gives us a vector. And we'll look at some other examples here as well. Okay, something like this. So each coordinate, xy, gets a vector attached to it. Okay, so that's our function. That's what we're going to be working with. It can work. We can represent them, remember, in various ways. So we can represent it with the I and j components. So the components of the vector, the force that's going in the x direction would go with the I vector. The component that's going in the y direction is with the j vector. So this is our x vector, either horizontally left or right. The I vector gives us up or down. And we can also use, I guess that's the ij form. There's probably have some other form for it. And then this, I guess, is the component form, where we don't have the I and j, but when we use these little pointy brackets, we know that this is a vector. And the first one is the component in the x direction, or the left, right, and the other one is the component in the up, down. And we can use shorthand and just call it P and Q rather than using function notation. There's scalar functions in two variables, so they're also called scalar fields. So multiple ways. Again, we can use it either in component form, we can use it as a function. So we'll go back and forth between there. And then what we're going to do is see that if we're in three-dimensional, three variables, it's very much the same. It's just we've got that extra variable, z. Okay, and we're in three-dimensional space. So again, the same thing in any point x, y, z becomes attached, that we can plug in those values to the function. We get a direction and a magnitude of a vector coming from that point. And then each point has a vector associated with it. Now, when we do this, we do not draw every point's vector, because it would just be, it would look solid, right? So we draw some general ones to say, okay, and then it's usually safe to assume that the ones close to a particular point are all going in similar directions. Something is happening. And again, we can represent it as a function. We can represent it as an ijk vector broken down by its components. And we can also do it in component form. Okay. Now again, some other notation they use here. They use a bolded x to represent that vector, which would be the xyz component form. So we'll go back and forth. So just be careful when you see this bolded x, that's referring to a vector. And so they can bold it this way instead of saying xyz. This is, so when we see the function sort of bolded, that's indicating it's a three-dimensional vector field. And so you'll see this. You could just call it bold f, you could call it f of x, you could call it just x. So let's take a look at an example. Let's start with two-dimensional field. So we're going to go with 2 dimensions. We're given this function, and we're asked to describe f by sketching some of the vectors f of xy. So just to kind of think of this, let's plot a point, choose a point, 0, 0. That's kind of boring because that's at 0, 0. Our vector becomes 0. So, but how about, if we're at it, how about just 0, 1? Or 1, 0, whichever. But so I'm putting in 0 for x, 1 for y. that gives me at the point 0, 1, it gives us a vector negative I, right? There's 1, this becomes 0, and so at 0, 1, I've got this point, the vector is 0, 1, the vector would be negative 1. Looks like it would just maybe be going down like that, although it looks a little different. We'll see. So let's follow through with this. So if we do with 1, 0, then we get just j, right? So y is 0, plug that in, 1, we get j. So draw that 0, 1 at the point 1, 0. That would be this one here. Oh, it's minus I, not minus j. I think I wrote the right letter, but so that's what I was expecting. Yeah, so for this one at 0, 1, I get minus I. Oops. Sorry, folks. So it should have, I should draw it this way, minus I going that way. So that's this one here. They did this one here, which is fine. And you can see we just point by point go ahead and plot them, and you can kind of see it's got this circular pattern around. So at 0, 3 we get this one, at 2, 2 we, so we could draw each of these. And I'll show you a tool that will allow you to take this function, an online tool, and actually draw the whole vector field for you. But this is kind of just giving us an idea of what's going on here. Things are moving in a circular pattern. Okay, and then they do 0, 1, we get minus I, so they again, they start going ahead and plotting all of these. Just like we do with regular graphs, we could plot multiple points, plug them into the function, get the vector, and then draw the vector. The other thing we can do, let's see if this will work. Let's see, how do I... It's not a clickable link, so let me back up. This one is, I think. So I found this, and again, you might find another one, but this is a two-dimensional vector field plotter. Let's copy that. Oh, here it is. I already have it. And so what was our function? I guess we're going to have to go back. Here it is, minus yi plus xj. So we can do that here. Minus yi plus xj. Notice you can mess with the scale here a bit if you want, but you can kind of see it's just going to go in circles. It's using a scale of 0.1. You could change it to maybe 0.5. It makes the arrows bigger, and you can see as you get further out, the magnitude increases as well. Okay, so this is what the vector field would look like. And again, you could play with the scale factor to kind of get it, because you get too many arrows, it's too much going on, you can't really see. So it's this playing around of how you scale it and everything. And this looks, pretty good. You got these circular things. So that's what that would look like. And you can use this for in the homework. They'll ask you to choose a vector field. So for at least the two dimensionals, you can enter it here and see what direction things are going. And then just sort of remember that you can pull these things out. Like you could say, okay, this point is 2, -1. Let's see if I plug that in, what's that going to give me? And you can see it's going to give you this vector that's coming right out of here. Okay. So let's keep going. And one of the things they noticed is that each vector seems to be tangent to the circle. Um, you see the circle, so it appears to be tangent to here, which would mean it would be perpendicular to the radius, right? And so they dot it with they do a dot product with that vector, and sure enough, it is perpendicular to the position vector, xy, and so it's tangent to the circle with the center at the origin, which would be square root of x squared plus y squared. The other thing we find with this is that the magnitude is the radius of the circle. So that's why as the circles, as we go further out, the circles are getting larger, the radius is getting larger, the magnitude of the vectors are getting larger. So there's this connection between what's going on there. Okay. We could also have, so this first part's just kind of getting us familiar with vector fields themselves, what they look like. We could have three-dimensional vector fields, and it could be like the flow of a fluid in a pipe. And so as the pipe changes shape, you get different volume, different flow patterns, different speeds. It might speed up, slow down. So if you go from constricted, should be going faster. As you go to a larger pipe, tube, that it would tend to slow down. So you could kind of see that this is a little bit larger. It's getting, the arrows get a little bit smaller as we get more room to move around. So this is a velocity field, say within a pipe. So three-dimensional, we'll be looking at some of these. Okay. And again, it does give us the speed at any given point and the direction it's going. And these types of things do occur quite often in physics. For this section, the last part we're going to look at is gradient fields. So let's talk first. What is a gradient field? Remember, the gradient, a gradient comes, we came up with a gradient when we took the partial derivatives of a function, and we took the x component was the x component of a vector, and the y partial was the j component of the vector. Okay, so that's what we defined a vector field to be, and we could just as easily have a gradient, a gradient vector. So the gradient is a vector from definition. We could also do it in three-dimensional space. If we had x, y, and z, we've got the partial of x, we got the partial of y, and the partial of z. So this is going to connect some of the things we did a few weeks back with partial derivatives. And then we're going to see in the 16.2, the next section, we connect vector fields with some of the integration we've been doing. Okay, so let's take a look at one example here. We're asked to find the gradient vector of one that's given. So we're in 2 dimensions, fortunately. I guess, we could go to 3 dimensions, not a big deal. Plot the gradient vector field together with a contour map of f. How are they related? So first we want, again, the gradient field. Let's see, is it upside down triangle? Or is it the other way? I think it's that, yeah. So the gradient of f is going to be the partial of f with respect to x, the partial of y in the j direction. The i's and j's always have problems. So looking at this, the partial with respect to x. So this first one, we take its derivative. It's going to be 2x to the first power, because the 2 comes down. Y is a constant, so it stays there. And then when we take the derivative of y cubed, since it's a constant, its derivative is 0 when we're taking the partial with respect to x. So that's our I component. To get our y component, we take the same function, but we're now going to take the derivative, the partial derivative with respect to y. So for this first term, derivative of y is 1. So we get, I'm going to put a parenthesis here just to group it, x squared. Then we take the derivative of the second term, which is going to be minus 3y squared. Subtract 1. So that's our partial with respect to y. And so that's the j component. Okay. And let's see. So this is our vector field. And I think they usually do a capital F to show that it is a vector field. Now we can go to this same tool, this online tool, to graph it. So let's do that. And give some room here, some overlap. So I can put in 2xy I plus parentheses x squared minus 3y squared j. Wow, that's a mess. So yeah, what we're going to do here, I think, play with this, go with kind of zoom out, make your scale where maybe 0.01. It's just so big. The other thing you can do is you can change your window. This is going from negative 10 to 10. We could, maybe go negative 30 to 30 in the x direction, and while we're at it, negative 30 to 30. So we're zooming out a bit. Or you could hit these pluses and minuses. I just saw those now. So you can, just so you can kind of get a view of what's going on. So it's the vector field's lower in here, not as much power, more power out here the further we get out. We can see from the north, it's like the wind is blowing to the south, and the south it's blowing to the south. So it's kind of coming through here. We've got some sort of side winds coming on, and it's kind of, that's what's going on here anyway. So it gives us a view of what's happening. Okay, so let's go ahead, and while we're here, we will, now the partials, that's what they got. Great, we got those. That's all we had to do is take the partials for x and y, and then the x partial is the I component, the j. Let's clear this writing out, and then they give us the vector field a picture, and that's kind of what we saw. They again, you don't draw every arrow. Sometimes maybe you want fewer arrows, but that's the same sort of, see, from the north it was coming, and it's kind of just blowing through there. But from the sides we sort of had, I don't know if you call them winds, side winds, and then in the middle it's kind of, going in a circle. So there's what we could call the contour map is these lines. So we're kind of getting directions, and notice the closer together that the lines are, the longer the vector is, the more magnitude, because that's a steeper. Remember, when they're closer together is a steeper change. And so when they're further apart, like in here, you get the smaller arrows. And for the homework, you just need to be able to recognize, you choose, it gives you several choices. You just need to be able to choose it. You don't actually have to draw them. Okay. So the gradient vectors are long where the level curves are close to each other, and short where the curves are further apart, again, because further apart is less rate of change. And that's what they explained here. Okay. And so there's also, we could call it a conservative vector field, as long as there is some kind of a function where we get the function f of the vector field is equal to the gradient. And this often happens, but not always. Not all fields are conservative, but we would call it potential function. And remember, when we're taking derivatives, sometimes if you have a constant, it becomes 0. So there's different things that can happen, but that's one concept we're going to have, is whether it's a conservative vector field or not. And this is our formal definition, that it's conservative as long as there is some function where the vector field is equal to the gradient. Okay, which is, remember, the gradient is a vector. All right, and I think that takes us to the end of 16.1. So we kind of, this is what I would have done on Wednesday instead of the test. Let me see what I can do as far as 16.2 and 16.3. We have those two sections where we're going to get into some integrations. I guess I could show my face. Anyway, we'll see you again tonight. I just at least wanted to get something posted and out to y'all to get you started. Thanks.